Please. Hi, everyone. I did not expect to be the first one, but I'm happy to get us started. So today I kind of want to not necessarily go very deep on one topic, but kind of give you a medley of different aspects on which how isolated quantum systems can reach equilibrium and even behave in a robust way out of it. And kind of like connecting it to the goal of the workshop, my perspective is that the development of quantum mechanics and of kind of these quantum coherent machines has allowed us kind of a new way and a new setting on which we can study many body phenomena. And what I want to kind of guide you today is kind of like highlight a couple of directions that I think are interesting and kind of like open questions, I think, in the field and moreover. And kind of hopefully there's some interesting back and forth, and hopefully that's interesting to you all. And so these are slides, but they're actually not slides. So my goal is to kind of like make a chalk talk. So please stop me if you have questions, concerns. The goal is to kind of like get the most out of this. It's not necessarily to rush through everything. So this is kind of like the outline for the first talk, the first part. So I kind of want to or on this one, not today, because today is also going to encompass lecture 2, is kind of guide a little bit how and why we expect systems to equilibrate. And this is kind of an incomplete answer that I'll give, because this is kind of like a work in progress. In many ways, it's undecidable. Why is it so pervasive? Why do we expect these equilibrium dynamics to work? And I think the interesting aspect is how do we kind of go beyond this equilibrium physics and actually kind of like see robust behavior that kind of moves us away from kind of what we expect in condensed matter systems. And so the outline for the first half is kind of divided into 5 parts. The first is kind of setting the stage, emphasizing that kind of different settings of dynamics have different expectations, and kind of like connecting exactly what I want to focus on today. And then 2 and 3 is kind of like teasing the idea exactly of what I mean by equilibration and thermalization. 4 is kind of like going to be just a simple description of many kind of thermalizing or non-thermalizing phenomena that people have observed, kind of hopefully maybe having a little bit of discussion there. And 5 might be the bigger of the chapter, is going to be kind of giving an intuition of like how we can use some of these ideas to actually build something that is robustly out of equilibrium, and understanding exactly why that's the case. Okay? And so let us begin. So what I want to start is by kind of like setting the stage of exactly the kind of dynamics that we want to probe. So in particular, like one thing that we often think when we take statistical mechanics is that we effectively have some sort of system that is coupled to a much bigger bath. And there we kind of have a picture of the dynamics of this many body, maybe even strongly interacting system through the lens of equilibrium of statistical physics. And the idea there is that the fact that there's kind of like this connection between the bath and the system allows energy, particle number, and all these other things to exchange between the 2 parts. And effectively, the description of our system basically wants to maximize entropy. Any information that I don't know about the bath is able to get into the system, or information that I know of the system kind of goes into the bath and gets lost, increasing the entropy. And this is kind of like, in this case, we can think of thermalization as kind of like a broad given. And this is kind of just arising from this interaction with the bath. And then kind of like when we think of like physical systems, this is our day-to-day experience, right? Too sensitive. When we think of a table, we think of a table at a finite temperature. That's what sets like its properties, its rigidity and whatnot. And this is kind of the way that a lot of like many body systems are studied. You need to take a material, you need to cool it down, and then you need to probe it in this kind of setting. What I want to focus on is a different setting that's kind of like motivated by the great advances of, let me just try to move this over here, of kind of like AMO and quantum mechanics, which we have a system where we effectively have some experimentalist friends work really hard to kind of isolate it from the outside world. Right? And here we're interested in understanding necessarily, this rectangle, let's try again. And here we have that the dynamics of the system is purely given by whatever conservative properties we have. So if we have, for example, a classical system, there's maybe some position and momentum, and I'll have some equations of motion that tell me how these properties evaluate change over time. But also in the quantum sense, we have that we effectively may start with a pure state, and basically on the Schrodinger equation, we basically have that this state evolves to a different time. Okay? And finally, there's a setting that I think we'll also hear about today, which is in the setting where we still have some sort of system that has been very much engineered and isolated from the outside world, but somehow we still have a window, and that window allows us to measure the system a little bit and perhaps like apply some sort of feedback. And this is kind of what we'll learn in the context of error correction, where we're actively removing entropy, and that hopefully allows us to see things like computation and whatnot. But the goal of what I want to focus on today is exactly this middle regime. And I kind of want to put a little bit of attention in your head, which is like if we think of a system as being very big, in some sense, even though we have this very clean descriptive notion of the equations of motion, there's still a sense in which we expect the system to thermalize. If I have a quantum system that is isolated but the size of the ocean, somehow the left side of the ocean still should approach some sort of equilibration, even based on how it interacts with the other side of the ocean. And that's kind of the tension that I want to explore and understand exactly how we can break this expectation down so we can see interesting phenomena that kind of manipulate the complexity of these large-scale systems into something that goes beyond equilibrium. Okay? That sound like a game plan? And so if we want to understand in some sense the pervasiveness of this equilibration dynamics, it's important to kind of understand exactly how equilibration goes to be. And I came prepared with a video. And this is kind of like a video determined by a classical system. So this is effectively n balls on a square potential, kind of the analogous of a free gas. And here we can get a pretty good sense of how equilibration goes, because even though all the particles on the left side of this box, after a while they kind of expand and they go around. And if I start the system on a completely different set of initial conditions, after a while that, for all intents and purposes, look completely indistinguishable. If I just took a freeze frame around now, you wouldn't be able to tell me where the origin of those particles came, even though all the information is encoded in kind of the precise positions at this moment and the ability of going back in time via the equations of motion. Okay, so the point that kind of like this highlights is that this notion of thermalization can be understood in terms of like a notion of typicality. In some sense, well, this is not the screenshot I wanted, but at the end of the day, like the state of the system looks like it is a typical thermal state. And so one thing that I want to kind of harp upon is that that is true because we're kind of interested in some sort of coarse-grained measurements. For example, if I'm interested on the particular position of any one particle, that will look very non-thermal. A particular particle is on a particular position with a particular velocity. But if I look, for example, at a coarse-grained quantity, for example, how many particles are on the left or on the right, what we see is that different initial conditions quickly kind of approach some sort of equilibrium dynamics. So the point that I want to emphasize here is that to understand kind of the equilibration in this classical system, there's some notion of coarse graining. And the one that I'm kind of emphasizing at this stage is in some sense of coarse graining in observables. And this is kind of like what we expect, for example, if I, instead of thinking of the position of any single particle, which is very out of equilibrium, if I think of the density of a gas or the amount of pressure that it exerts on a wall, the fact that it averages over the many particles allows statistical physics to kick in and give us some notion of like average that allows me to describe my very complicated many particle system in terms of effectively a pressure and a temperature, for example, right? But one interesting thing is that we can also think of different kinds of coarse graining. For example, we can also think of a coarse graining in time. And there we could imagine that basically a particular configuration, initial configuration of my system, is effectively going to meander across phase space and try to occupy as much of phase space. And if I'm trying to kind of like sample this in time, maybe with a slightly brighter color, I get that in some sense, the average of my samples in time effectively are given by my equilibrium value, right? And this is kind of like, in some sense, the fact that my system is exploring the entirety of phase space is what allows me to see this equilibration as an ensemble level. Alternatively, you can also think of kind of like a coarse graining in terms of initial conditions. So if instead of having a single initial trajectory, I think, for example, of the dynamics of a small piece of phase space, which is not showing up, so let me draw it, some sort of like ball, a probability of configurations. If I have my system to be chaotic and ergodic, what this ball is effectively going to do is it's going to stretch and basically, even though the area isn't changed, is going to basically spread tentacles across all of phase space. And if I try to coarse grain and measure properties across this, the fact that I have this chaos and ergodicity is again going to give me a notion on which I can talk about an equilibrium of this particular configuration. Okay, so here it's kind of like, again, it's the idea of thinking of a particular snapshot. I need to be very careful what I mean by equilibrium. To talk carefully about equilibrium, I need to think of some sort of coarse graining, because the properties of each individual degree of freedom are very different from what I would expect at equilibrium. Okay?
How are you defining the equilibrium in time? It's moving in time, it's dynamic, right? So
that's a good question. So what you want in some sense is that you have some property of your system, and whatever coarse graining you do, that this effectively becomes time independent. And this time independent value is kind of related to what you expect out of the Gibbs ensemble.
like an ergodic system.
Exactly. And this is kind of like the way that we connect it to equilibrium. And this is kind of already what we see over here, where we started with a system that's highly out of equilibrium, but as time progresses, it approaches the half value of particles to the left versus particle to the right. And you see that there's some fluctuations that have to do with the fact that we're working in 200 particles rather than 10 to the 24. But the size of those fluctuations relative to the signal effectively diminishes and diminishes. Good question. Any other questions? Awesome. So I think more broadly, maybe a different way also of saying is that what we want is that our observables in time effectively approach some sort of equilibrium value with some sort of oscillations, fluctuations, and those fluctuations should be smaller than the properties of the signal that I care to measure. So if we think, for example, of energy, the energy is usually an extensive property, but these fluctuations, if we think of statistical physics, are usually something on the order of the square root of the number of particles. And that is what gives us like the fact that we don't matter when we have gas in a canister, certainly the pressure doesn't shoot up, because the probability of all of the particles suddenly ramming to the right side of the tank is very small. Okay? So interestingly, and maybe the point that I want to now talk about is how does this picture change when we think of quantum mechanical systems, right? And in many ways, quantum mechanical systems have the same feature, where I take a state and I evolve it. And if I know the properties, if I know the wave function at the start, I know the Hamiltonian of the system, I can predict the evolution of the system to late times. The one thing that is important about a quantum system is that the sum is more than the whole is more than the sum of its parts, right? So whereas in a classical system, the properties of the whole, I can basically zoom in on the left, and the state of the particles on the left are in some sense tensor product with the state of the particles on the right. In the quantum system, dynamics can generate entanglement, and that makes that's no longer true. So what do I mean by this is that we have a wave function that is described on a big system, and if we then look at the evolution of this wave function across the whole, maybe at the start, it is a tensor product of something that's on the left and on the inside and outside of the subsystem. Under the dynamics, effectively entanglement is going to be formed, and at the end, the state is still in a pure state, but it has built up some entanglement that I can kind of like describe in this form of kind of Schmidt decomposition, right? So crucially now, if I ask properties, for example, only of the system on the right, only of like the system A, then I effectively have to trace out over its complement. And even though I started with a pure state globally, the result can be a very mixed state that can look very thermal. Right? So the intuition is that I start with a spin system, for example. I start in a product state, maybe up, down, up, down, up, down. And then if I focus on this particular subset, magnetization is going to slosh around back and forth. But basically, if I look at the magnetization within the subsystem, it's going to be, all the properties of the subsystem are effectively going to be exhibiting a mixed state feature. I think the cleanest example of this is kind of like the bell pair. So if you think of a particular wave function that effectively looks like a bell pair, the crucial aspect of this is that once we trace out the complement, the system effectively looks locally as a mixed state, because with 1/2 probability, I measure the complement in up, and I get that my system is going to be in up. And with 1/2 probability, I'm going to measure the complement in down, and I get it down. And this is actually the fully mixed state with the most entropy possible. The other feature of quantum mechanics is, in some sense, the dynamics are actually quite, yeah.
I mean, the two state, how is it related to the original?
Oh, yeah, that's a good question. So usually what you want to define is not, that's a good catch. Usually what you want to define is that this approaches the trace of the complement of the whole system. And then you don't necessarily need to worry about how to define the Hamiltonian on this subsystem, because this also takes care of the boundaries. Good question. Any other questions?
Yeah. Looking at the density matrix, but does the density matrix, like the density matrix written here, does it have the information about the entanglement, or is it lost it after tracing it out?
So the entanglement of that you measure between A and its complement is effectively going to be the entanglement of this. Because the whole system is in a pure state, you know that the total entanglement has to be 0. So this entanglement, this form of entropy that you measure by doing this is just entanglement. There's no thermal part.
Okay, so like you construct the entanglement entropy from the row A, you will get 0.6.
Yes, exactly. Okay. So this kind of tells us that there's kind of a feature on which, unlike the classical system where I took one single pure state and I evolved it and I needed to be careful about coarse graining, whether in observables, here it tells me that a single pure state of a quantum function can actually approach an equilibrium state at late times. Okay? And we can kind of like formalize this a little bit by looking, for example, at the properties of an observable O. And the reason why, in some sense, quantum mechanics is easy to compute this, easy in quotes, is that the Schrodinger equation is a linear process, right? So the Schrodinger equation tells us that the evolution of the wave functions follows something of this kind. And so when we think of the expectation value of the operator at a later time, it's just the wave function evolve sandwiching the operator. And this particular structure tells us that we can actually compute the dynamics of the wave function in terms of the eigenstates of the system as something like this, where I'm setting h bar to be 1, and En is effectively the energy of eigenstate by n. Okay. So if we work this out, what you end up is that you take this formula and you put it on both sides, and you end up on the double sum of effectively, I'm going to do this Cn on the left, Cm on the right. Then we have e to the minus I Em minus En. And then we just have phi n, the operator phi n. Okay? Does that make sense? So this is effectively just a matrix. So we can just call it of n of m. And this double sum has an interesting property that when m equals n, the time dependence that should be here kind of drops out. And so we can actually write this very cleanly as kind of C of n squared O of n plus n different from m, Cn, Cm dagger, e to the minus I delta Enm, because I'm running out of space, times O of nm. Okay. So this kind of tells us a couple of interesting properties about the dynamics of this quantum system. Let me just organize a little bit the space here. Because it tells us that kind of like all of the dynamics are.
So when you write down, so going up a bit, rho rate, proportional rates, some sense, it's inherently assumed that with that data, it's inherently assumed that there's a path for system A because you have the limit temperature.
No, so that's a very good question. Not necessarily. So here, what we want is that this is how we, in principle, define equilibration, is the fact that there is a thermal state that you approach. So in principle, there isn't a bath. This bath depends on the conditions of your state. And to understand that, we think of like temperature is a conjugate variable of energy. So the thing that determines this particular temperature is going to be the condition that the energy has to be constant. Right? So that tells you that the energy of your initial state is going to be the energy of your final state. So you expect that effectively, if you look, for example, locally, that the properties is that your system is going to satisfy this with a particular. So in some sense, the energy density sets the temperature, the same way that if you do the same experiment with different conserved quantity, for example, magnetization or charge, the amount of charge sets the chemical potential. Make sense? So this kind of sets a very nice kind of way of understanding dynamics, in that the system, the orient kind of like all of the properties that I care to study about this of the equilibration are encoded on a couple of properties. So let me just say that and emphasize this point, that if I want to say that the system has reached some form of equilibrium, I want this, that as time goes to infinity in the large n limit, that this approaches kind of the equilibrium value, which might depend on the energy of the initial state of some other global property of the initial state. But crucially, it shouldn't depend on details of the initial state. And this kind of tells us that if I want this to be true, this is time independent. So I need that the time dependent part of my system should effectively disappear. So as time progresses, all of these kind of like oscillating terms need to effectively cancel one out in a very efficient way. which we expect to happen if those energies are kind of incommensurate and the value of these O's are small, right? But in the limit where the second term kind of like disappears, this also is saying something about the early term, because it's telling us that the properties of these diagonal terms of my operator actually have to encode properties of my equilibrium state. Yeah. And so far, it seems like I only talked about O and properties of how the operator intersects with the Hamiltonian. But there's also the fact that I need these coefficients C to, in some sense, be well behaved. Because if I started, my physical system that I want to probe fundamentally has a very complicated distribution of eigenstates, maybe it becomes unclear what is the notion of energy, what is the average energy, and factors like that. So in some sense, and maybe trying to like connect this maybe with a broad picture, we expect that the dynamics of such property as a function of time is that at 0 time is going to have some particular behavior corresponding to the particular initial state that I chose, and eventually it's going to like approach a value, maybe exhibit some small fluctuations, and this is going to be what we think of some form of equilibration time of my system. Okay. And as I alluded, there's kind of like 3 elements that matter as one analyzes this. One is indeed that we need the dynamical part to die down. Maybe let's not use just such strong words, to go to 0. And that kind of tells us that O of n of m are kind of like small and can't be too big, because this sum is over many, many parameters. At the same time, it tells us that the energies, in some sense, have to be incommensurate. Because otherwise, different oscillations can kind of like cancel one another and make sure that there's additional structure on the dynamics of this observable. The other is that in some sense, these diagonal terms O of n have to kind of encode properties of my equilibrium dynamics, and so they must be, in some sense, capturing features of the energy density of my initial state. And third, for this last point to make sense, we also need that the distribution of these parameters Cn is kind of like well behaved. And what I mean by that is, if I prepare an initial state that is feasibly I could prepare in real world, in some sense, the distribution of coefficients has to be, in some sense, peak around the average energy of my state, so that this sum is not very ill-behaved. I.e., I don't want, if I prepare a particular initial state, I don't want it to be an equal superposition of the most excited state and the ground state of my system, because then I don't even know how to define an average energy and what exactly these properties become. Okay. So a lot of these elements are kind of like hard to make statements on, because they depend on a lot of features of my system. They depend exactly on the Hamiltonian, which determines the structure of my eigenstates and my eigenvalues. It depends also on the observable that I use. Maybe some observables may display this trend, but others may not. And it actually also depends on the properties of the state that I choose to look for equilibrium around. So this kind of tells us that, in general, answering this question is quite hard, and there are proofs that, in general, there's no procedure to say whether a particular state thermalizes. One could cook up very complicated Hamiltonians that prevent us from saying that. And indeed, all proofs about how the thermalization of quantum systems behaves is very suitable to particular settings. I think what are the features of that take into account features of the eigenspectrum, feature of the operator, for example, locality, and so on and so on. I want not, yeah.
Right now, you just do not take any degeneracies here in the red. It's like completely non-degenerate spaces.
Yes, I'm assuming that that's the case. And that's why, in some sense, if you think of the harmonic oscillator, there's no way that the harmonic oscillator can equilibrate. And that's one way of understanding why the dynamics are periodic for all time. The harmonic oscillator has these degenerate, all the gaps are degenerate. So you have that second term will never effectively average out and cancel out. Make sense? So in general, as I alluded, it's really hard to make predictions about whether or not systems thermalize. And there's been a lot of effort trying to understand the class of systems that thermalize. One way that people have been thinking about is using the eigenstate thermalization hypothesis. Eigenstate hypothesis. Which is in some sense like a very strong statement that people have made about quantum systems, which is like in quantum systems that exhibit, that are non-ergodic, there's actually, one can show that, or one can argue or kind of hypothesize that indeed these matrix elements that I'm describing here, sorry, let me be a little bit more precise, that the matrix elements with respect to the eigenstates of my system take a form where there's a diagonal component that depends on the energy of my eigenvalues, plus some fluctuations that usually are dependent on the entropy of my system. And there's always a factor that depends on the energy difference times some random variable. And this is kind of like the strongest claim, the strongest statement that you need to kind of see this thermalization, because it tells us that the structure that I alluded on these parameters is actually something that is true for a generic observable that you're interested in, and at the level of each eigenstate. And in some sense, each eigenstate itself represents a thermal state, because it's basically all the properties are dominated by this particular matrix element, which by fiat is capturing the equilibrium behavior of the system that you care about. So this is usually a Gaussian random variable. So this is kind of like, in some sense, you can think of an ansatz because an hypothesis, and something that was introduced, I think, in 1994 by Srednicki. And it's kind of been the way that people think about non-ergodic, chaotic thermalizing systems. And the idea is that if you satisfy ETH, your system is equilibrating, provided you prepare some reasonable initial state. And this is something that people have checked that a lot. Not only do most interacting ergodic systems satisfy ETH, indeed you see that the system eventually thermalizes. So before going into that, I want to emphasize a point, which is that which is kind of like, I've been assuming a notion of thermalization with respect to the Gaussian.
Could you get as a classical limit now, or the minimum entropy?
Say that again.
Could you get the classical limit with the entropy is minimum?
What do you mean entropy in this context?
I mean, a classical trajectory with minimum action or maximal entropy, or something like that. Could you get to here from to get back as a classical regime?
Not clear, because not all quantum systems have a simple classical mapping. Like there's no clean mapping on which I take spin 1/2 And I think of, like, as I take the S to infinity limit, that becomes a very different kind of model. So it's not always clear that you can build like a classical phase space that allows you to then build kind of like a classical correspondence. Does that kind of answer your question?
Yeah. This reminds the Feynman integral when you have an exponent of that.
Oh, okay. Oh, no, I see. No, I see. Okay. Yeah. But this, in some sense, is just a statement of the static properties of your Hamiltonian. So it's not clear necessarily how you frame. Maybe you could frame that kind of like a Feynman integral to infinity and back, but I'm not sure if necessarily have to do that. Awesome.
So what's with the timescale in which it equilibrates at least?
So that's a good question, and that highly depends on the nature of the system. So, for example, there are systems, and let me punt that question in a bit. Sounds good? Because I think I'll give you a straighter answer once I comment on a couple of things. So far I've been talking about thermalization as kind of like how a system starts looking like it looks like the Gibbs state. But a question could be, is this the only notion of thermalization that we can have? Right? So this implicitly, for example, assumes that my system has a static Hamiltonian that describes the dynamics. I could ask the question, what happens, for example, if my Hamiltonian now has some time dependence, or even it's kind of like periodic in time? In this case, I don't have a notion of energy that becomes conserved. And then this notion of temperature breaks down. There's no one quantity that I know a priori that I can use to kind of serve as my Lagrange multiplier. So in principle, if I have these kinds of dynamics, and I'm emphasizing this because we'll come back to it in a bit, you actually expect a different kind of thermalization, where your system goes to the fully mixed state. Now, I see some puzzled looks.
Was also a mixed state.
But this is a fully mixed state. So I drive the system, and regardless of my initial state, I'm saying that locally, it will look like a fully mixed state. And we actually have a little bit of intuition about this. If I have a system that I'm shaking, effectively, I'm allowed to pump energy into the system. And as the system interacts with my drive effectively, I'm going to maximize the entropy of this and pump as much energy as possible. And that's effectively going to drive my system to the fully mixed state. Okay? But we can also have a different setting where I might have a system that not only has a conserved quantity of the energy, but maybe it has some magnetization or some charge. Let me say Q for charge and magnetization, the sum over SC. And now, the same way that I define temperature with respect to the Lagrange multiplier of the conserved quantity, I expect that my thermal state that I approach is going to be something that effectively knows about all of these conserved quantities. So in this landscape, there's kind of like a world where the type of thermalization that I expect depends on the nature of the dynamics, once again. And there's systems that thermalize either a little bit, because they're constrained by the dynamic properties, or constrained not so much, or are not constrained at all, right? So there's a level of which, depending on the properties of my system, I can have different levels of thermalization, how much I can go. Interestingly, we also know that if we have a conserved quantity like a magnetization, it induces other kinds of limitations. For example, if my energy or my charge is local, charge has to move through the system. So it has to diffuse or ballistically move. And that tells me that my equilibration time has to effectively scale with my system size. But if I don't have any conserved quantities or no local conserved quantities, now my equilibration can be much faster, because now the system locally just needs to mix as much as possible with its neighboring states. So there's kind of like, maybe this is why I was trying to punt the question, is that there's kind of like a two way of thinking of like the nature of the thermalization, which is like, how much do you thermalize? And how fast? And there's kind of like what the goal of this is to emphasize that there's effectively a landscape of thermalizing phenomena as one moves across. So I kind of put everything at once. So maybe I kind of like discuss a little bit of some of these things, and hopefully maybe this also like highlights a little bit more what I mean by these properties. So maybe let me start from the right side. So I kind of emphasize the thermalization, that there's different degrees depending on how many conserved quantities there are. And in that sense, kind of like the strongest form of thermalization will occur when my dynamics are as random as possible. I take my state, I do a random unitary, I then pick a different random unitary, and then I then pick a different unitary. In some sense, this kind of like notion of random unitary circuits allow my system to equilibrate to the infinite temperature state very effectively. If I have some sort of time-dependent Hamiltonian, now I may not have a conserved quantity, but I have quasi-energies that are conserved, and I'll explain this a little bit more. And that further has like a notion of the fact that I have those eigenstates suppresses some of this equilibration dynamics. And then as I move further to the left, I'm adding, in some sense, constraints to my system or features to my system that either slow down how fast equilibration can happen or kind of limit the kind of amount of Hilbert space that my dynamics can probe and the kinds of equilibration that I can see. Whether it is just thinking periodic, moving on to kind of interacting systems with maybe additional conserved quantities, Fouquet prethermalization, which I'll discuss later today. But then you have other regimes where your system adds so much constraints that it starts not thermalizing with respect to particular initial states or particular observables that you care about. And this is when you start seeing these kind of many-body stars, which are kind of particular initial configurations that exhibit very long-lived oscillations, but are imbued in a thermalizing, in an otherwise thermalizing Hilbert space. There could be properties where the Hilbert space kind of fragments into different subsets that can equilibrate between themselves but not across. And that again adds a different layer of suppressed thermalization. And then we get into the regime where we can have like an extensive number of conserved quantities that either emerge because of the properties of my system or kind of like because of disorder. Okay. So
Just
yes.
short. Like MBL in this case, maybe I get biased because a colleague of mine did his full PhD disproving MBL. But this is just like on time scales that do not exist. So like when we talk about non-thermalizing here in this case, this is just on like time scales that are relevant for like us here in an experiment or whatever.
That's a very good question. So let me maybe explain that to everyone. So MBL is kind of like a proposed phase of matter that is robust and that exhibits a thermal behavior. So I was going to go into that later, but the short answer is like there could be what current numerics demonstrate is that there's an exponentially controlled time scale that is controlled by the exponentially by the disorder strength of your Hamiltonian, and then understanding whether as you move the disorder further along, whether it becomes a true phase or not is something that we don't have the tools to answer. So for now, it's either infinity or the time of the universe, and we don't know how to distinguish those either in experiment or theory. So I will not make a claim about the stability of MBL, but I will talk a little bit about the phenomenology and how it can help us understand some of the observations that people have seen and kind of motivate some of the studies that people have done. So let me kind of like jump into that because I will kind of introduce it as I'm trying to build this notion of a discrete time crystal as an example of the kinds of physics that you can get in these isolated many-body systems once you're able to move past this kind of like fate of equilibration and have a very long window, perhaps infinity of time, where the system fails to equilibrate. So let me start by kind of like defining what I mean by this time crystal. So I will define it in a way that I think is the quickest, which is when we think of a normal crystal, the way that we define it is that, yeah.
So it seems to me that depending on how many how many conserved quantities are there in the system. That is what dictates the degree of thermalization or the time scale of thermalization. So like if you have infinitely conserved quantities, it won't thermalize it.
Not always. So their system with like an extensive number of conserved quantities still show aspects of thermalization. I'll talk about it later today. There's also systems that have the same number of conserved quantities and they have very different thermalizing behaviors. So you could have like a system that even between those two either displays ballistic or diffusive dynamics. And then the thermalization time either scales linearly or quadratically with the system size. So, and I'll also talk about later today how you can even like add an additional parameter, and in a way similar to this exponential dependence on disorder, you can exponentially control exponentially the times on which the system thermalizes. Any other questions?
In the list of everything from non-thermalizing to fast trauma thermalizing, is there? It seems like there might be some pattern in the focus between the eigenvalues that are strictly in the bulk and extreme eigenvalue behavior, and the ability to reach thermalization.
Yeah.
Is that something that is well characterized in kind of the flow chart or in I guess the theory as a whole?
Yeah, so I think like in general, like there's, then it depends on what you mean by thermalization and what you mean by being happy with seeing thermalization. Because if the request that you want is that for any certain subset, for any initial state, that it has to thermalize, the presence of those extremal eigenstates will probably mess that claim. But if you want a typical statement about typical eigenstates, the fact that you have some that might not thermalize then gives you some wiggle room. So there's kind of like these notions of like strong and weak ETH and kind of observation of like how the conditions of thermalization depend of exactly how stringent your condition on thermalization is. Does that kind of answer the question?
Yeah.
And I think like what I want to kind of convey with this point is that like, it's not to say that because this is such a hard problem, I don't think that there's like necessarily a consensus question that encompasses all forms of thermalization. And as we find more and more varied dynamical phenomena, I think it allows us to sharpen different distinctions that allows us to build kind of like this set of labels. But like any characterization, it's incomplete. And a lot of this is not as sharply defined as phases of matter are, because we don't have kind of like a discontinuity in some of these features. A lot of these phenomena might even thermalize at very late times. And so there's kind of like a crossover into a non-thermalizing behavior. Does that kind of answer the question? So keeping an eye. So I want to kind of like introduce this discrete time crystal, and I'll do it in analogy to a normal crystal. In a normal crystal, we define it with respect to the fact that we have some sort of Hamiltonian that depend on the positions of my atoms on my lattice. And this particular Hamiltonian has a symmetry where I can take all the positions and shift them by a little bit, and the Hamiltonian stays the same. And this gives me a continuous translation symmetry. A normal crystal happens when suddenly, even though this is the underlying set of equations, the underlying interaction in my system, if I look at the density of particles, it no longer respects this symmetry. And if I take my lattice and if I look at my density at a particular point, and I look slightly to the left at the atomic scale, suddenly an atom isn't there. So the homogeneity that I would expect from the equations of motion disappears. And so it's kind of, again, it's the idea that this symmetry gets broken. And I went from in this case, a continuous symmetry into a discrete. But the idea of a time crystal is you change normal and you put time. And instead of position, you think of time. I have a Hamiltonian that maybe is time independent. So if I shift it a little bit by some delta t, it should be the same. But somehow I have a robust notion on which I have the expectation value of an operator and that expectation value of the operator is not symmetric under this transformation. Okay? And this would be a continuous time crystal for multiple reasons that I do not go into, don't want to go into detail now. Turns out that this doesn't work this way, and you cannot have this continuous time translation symmetry breaking time crystal. The intuition is that otherwise you take the ground state and that is going to have some oscillating dynamics, and then you could build a perpetual machine by trying to extract energy from those dynamics. So what we want to think is actually a case where instead of thinking of a small continuous transformation, we think of a discrete transformation, and then we can still have the notion on which our system goes from a discrete symmetry, breaks that into a bigger discrete symmetry. And for those who do more condensed matter, this is kind of the analogy of a charge density wave. If I'm allowed to kind of make a picture, you could imagine that as a function of time, you could have a Hamiltonian that maybe looks like this. Yet the observable that you care about, and let me make sure that I get this right, does something like this. Okay. So the observable has a periodicity that's this large, whereas the dynamics of the system has a periodicity that is this large. And that is what I mean by time translation symmetry. And we're going to build it by using MBL, and I'll now put some caveats on following this up. So one way of, I will start by kind of like changing gears a little bit and talking a little bit about many-body localization. And then once we introduce the key elements, it'll be easy to see how to make time crystals. And that color does not look as nice over there as it does over here. What?
You cannot see it.
Yes, so it looks much better on my screen. So let me try to find a slightly better one. Is that better? Okay, that's better. Okay, we'll make it work. Okay. And the idea of this, I'll kind of like motivate it within a particular example. So consider the following Hamiltonian. It's kind of a complicated Hamiltonian, but hopefully it's kind of the prototypical Hamiltonian for these kinds of systems, where you have some form of interactions between different spins, and then you put a large amount of disorder that kind of like couples only to the Z magnetization of the I spin. Okay? So in the limit where I don't have interactions, if I destroy this one, all the quantities of motion, all the eigenstates are labeled by the total spin, and each spin is effectively a conserved quantity. You can think of this as kind of like the free particle limit that is not very interesting. The question, and kind of like addresses to your point, is whether this free particle limit, where excitation are localized, stays true the moment I add a little bit of perturbation. Now, I don't want to discuss whether or not this is true at the infinite level, but I just want to kind of give you a picture of the phenomenology that we associate with this MBL phase. And in particular, what we imagine is that as we tune on this J, and J goes from 0 to a finite value, maybe let me call it epsilon, these local conserved quantities get effectively a little bit dressed by the fact that there's interactions with other degrees of freedom. And the way I'm going to call this is that they become these other kind of operators that I'll call tau, but crucially to all aspects, tau kind of looks like the original sigma z, and then it has some corrections that might depend on the smallness of my parameter epsilon, right? And if such quantities exist, let me move this up. Sorry. If such quantities exist in a robust way, then, and what I mean by that, in a way that h tau I of z equals 0, that gives me a way that I have local constants of motion that allow me to define in what sense my system does not thermalize. And the reason why it doesn't thermalize is that if these operators are local, mostly within a particular site, if I encode a particular bit of information there, it's going to have a large overlap with this operator, and it's going to live for a very long time. So if one is to draw this, we might start our system in a particular configuration. And if I look at very late times, these spins are no longer exactly localized on one particular site, but they mostly still look up or down with some particular wingspan, some localization length, I'll call it C. Okay. So the important part of this MBL is that this is predicted to be robust, i.e., it doesn't really matter like the nature of my disorder if it's large enough and the interaction is small enough compared to it, then this should be robust. And for different choice of parameters, there's simply a different choice of localized integrals of motion. No, this is meant to be the tau. So let me maybe draw this a little bit better. So basically, you have these are your spin degrees of freedom, and then you have these tau degrees of freedom that are mostly localized. And so you should think of them of effectively like some exponential that has mainly still aligns with the original. So when you prepare this particular initial state, for example, it has a large overlap with a corresponding eigenstate where these tau operators are pointing along the same direction. And this will not be changed under the dynamics. Of course, every piece that doesn't have overlap is going to dephase and move away, but the bit that has a strong overlap is going to stay fixed, and that means that at late times you'll still have the same configuration. Okay.
The interaction that you've chosen, it looks to me that it's like a Gaussian strip. That's why you have so many.
What do you mean Gaussian?
You have two operators contributing to the.
Oh, sorry. In principle, this becomes many-bodied, but the point is like the higher the weight of this term, the smaller the coefficient in front. There's an additional, for example, epsilon q, epsilon squared. There's now sigma z, sigma z, sigma z, or sigma x, sigma y, sigma z, but they effectively decay exponentially, and that's what leads to this localization length scale. Okay. And actually, once you have, if you believe this, and kind of whether it's exponential, it's infinite, or just exponential in the disorder strength. Let me define disorder strength as kind of like how much I'm allowing this random field to be tuned by. Now you kind of have the ingredients for seeing this this time crystal. And the way that we can prepare one is to think of the following protocol, where you take your system and you evolve it under this NBL Hamiltonian for a bit. And in the perfect world, what you'd want to do is effectively apply a pi pulse with respect to these new degrees of freedom, which you call tau. Okay? And if you're able to do this, if your protocol here goes from 0 to time, and here it goes from tau t to t plus pi. So let me make sure that I get this right. Pi over 2g. Then the dynamics of your system is going to be the unitary that describes the dynamics of your system is effectively going to be e to the minus I h MBL t. And then you basically, this operation is just going to basically flip all of your degrees of freedom from up to down. Okay? And you can now understand why this has a discrete time response, because if you started your system in a particular spin configuration, the evolution under this element is basically going to lead to a phase, but then applying this pi pulse is effectively just going to flip all of your spin configuration, and that's still not good. It's effectively just going to flip all of your spins. And if you do another one, you go back to the original configuration. So even though your system has some periodicity in tau, your system only goes back to itself after time to tau, breaking the discrete time translation symmetry of your drive. Now, to do this, this feels very fine-tuned. The crucial part of like the robustness of MBL is that now it actually doesn't matter if you have tau or if you have sigma. And it doesn't matter if you have G or if you have G plus some epsilon. In some sense, the robustness of these local degrees of freedom means that the same phenomenology extends as you go to, as you change the parameter of the system, allowing you to define a proper phase of matter that is robust. Okay. I think I'm running a little bit out of time. So one thing that I'll make note here is that one way of understanding this phase transition, why it's fundamentally different from like symmetry-based phase transition, is that this is purely in the dynamics. My system doesn't necessarily have to have an underlying symmetry to display this kind of order. This kind of order actually manifests itself in kind of like what is known as pi pairing. So if you look at the eigenstates of this particular, of the unitary, so you could write it as something like this. What you find is that in the time crystalline phase, for every phi 1, you find exactly phi 1 tilde eigenstate that is whose eigenvalues tend to be exactly shifted by pi. And it's kind of like that locking in this kind of spectrum of this Floquet operator that allows you to kind of like see the subharmonic response. And crucially, it's a property that happens across the entire spectrum. So I think this was kind of fast. So if you have questions, ask me about, but I'm running out of time. So I just wanted to kind of finish by kind of showing you a little bit some references and kind of pointing out to some of the ways that people have seen this kind of phenomenology. I think the first paper to see this form of like pi pairing and kind of proposing it in terms of a phase was kind of this paper from 2016, where they drew this phase diagram in terms of like the properties of the eigenstate. But then there was the observation that actually you don't need an underlying Z2 that here they assume. Actually, just having this time translation symmetry allows you to stabilize this behavior and have a fundamentally different kind of phase of matter, where the dynamics, the properties of the dynamics map onto this property of the spectrum. And finally, there's kind of like the way of like studying not only this phase, but also transitions of it in kind of experiments. And since then, people have seen this in experiments. There's kind of like already 4 platforms. The first two on the left were kind of like the pioneering works, where they effectively saw time crystalline behavior either in an ion trap setup or in a solid state platform of spin defect in the solid state. And more recently, there was a little bit more careful analysis of making sure that this kind of like comported with the expectations of MBL, and those were again in a different kind of spin defect, in this case nuclear spins. I shouldn't point on my screen, I expect you guys to see. And also in the context of like these superconducting qubits. But the point that I want to conclude and kind of like finish on this note is that the ability to study this kind of behavior and this kind of phenomenology only arises from the ability to manipulate an isolated quantum system. All of these features, this kind of pi pairing and the stability of these phases, fundamentally requires you to have an isolated quantum system. And the moment you couple to a bath, the thermalization times are now dictated by the strength of your coupling to the bath. And this is kind of like the note that I want to end on, which is like being able to isolate and study these kinds of systems allows us kind of a new lens with which to explore dynamical phenomena. And this time crystalline is kind of like the cleanest example. But as I kind of hopefully convince you also with this kind of landscape, there's an entire, in some sense, dynamics has to be more complex than statics. So there's an entire landscape of phenomena, thermalization dynamics, dynamical phenomena that kind of arise, and I think is still something that we're exploring, and with many intersections within AMO, quantum information, and kind of like mathematical physics. And I'll kind of leave this at that, and I'll thank you for your time.
Your questions, but there's time. But of course, Francisco is going to be around. Over dinner, over lunch, there's no escaping. So